David Hanley. He is with David Hanley Environmental. He comes prior years of experience at Geosyntec, and he is another panelist that has a lot of extensive experience in mitigation design as well as implementation. And he is going to talk to us about pressure field extension testing. So he was also part of the AVIP conference. As a plug for AVIP, you see a number of these presentations. If you want to learn about the best of what's going on in VI in a very concentrated, highly informative environment, that is the conference to attend. So, David, handing it over to you.
Thanks very much, Peter. So this presentation was on pressure field extension testing, specifically in mitigation systems on new construction buildings. So we looked at data that we've collected at more than 50 new construction buildings with mitigation systems where we've performed this pressure field extension testing and broke down the data in different ways to look at it and see what conclusions we could draw and use that information to be able to improve VIM's design in the future as far as performance and efficiency. Um, so some background on what pressure field extension testing is. This is a type of testing that's used to verify that a venting system can get influence throughout an entire subslab. After the subslab venting piping is installed within usually a gravel layer and there's a barrier over top and then a slab is poured, we'll go in and put a vacuum on the VIMS riser pipes and take measurements of the vacuum influence in the subslab at different distances away at test ports through the slab. We'll use that data to confirm that the system can be effective and provide vacuum influence throughout the slab, and also to look for things like inconsistencies and issues with the venting system. So this testing can be performed both for active systems that are planned to be active and also for passive systems to be able to give data to confirm that the system could be effective if it ever became active in the future, and to be able to appropriately size a fan to put on those risers. So this testing is a required component of the ANSI-ARST CC1000 design standard, which is the design standard that we use to design our mitigation systems. It's also recommended for new construction buildings to be performed as part of the VI best practices roadmap that Andrew discussed earlier and was released earlier this year. Just a couple photos next showing the typical setup for pressure field extension testing. We've got a riser coming out of the slab, and then that's connected to a manifold where we've got a vacuum gauge to be able to measure the applied vacuum, port to measure airflow within the manifold so we can calculate, it measures air speed so we can calculate the airflow rate, a few valves to be able to control the airflow and the applied vacuum, and then our fan to be able to apply the vacuum. And then finally here, a test port on the right where we take the vacuum measurements at very low levels down to 0.001 inches of water column. So the data set that we evaluated for this consisted of systems that we performed testing on during the past 3 years. This included 55 new construction buildings, 932 data points were collected from 164 risers, more than 300 test ports. So I want to acknowledge this photo shows my colleague Joe Gentlecore. He's the one who collected most of this data, which was quite a bit. Before we dig into the data, just an example of what we're looking at as far as a VIMS layout. So this is a design for an apartment building with 2 risers, one here, one over here. The pink dashed line represents collection piping in the subslab. The green line are solid pipes that go across footers. The footers are the red dashed lines here. And then we've got test ports that are our purple triangles. So we measure the distance for those test ports to the riser. And also note in cases where we're going across a footer that can affect the vacuum influence. So we'll take a look at that as well. Here's all the data just plotted on a graph with distance from the riser on the x-axis, and then the vacuum reading at the test port on the y-axis. not especially helpful to look at it in this way because we test at different vacuum levels, applied vacuum levels. At each riser, we might test at several different levels to be able to see changes in vacuum influence. So we can normalize this data by taking the vacuum influence measured at the test port and dividing it by the vacuum that was applied at the riser. So that tells us the retained vacuum on a scale from 0 to 1 versus distance. So if we normalize the data in this way, it allows us to break it down and more easily compare different tests that were done. So in the full presentation, we gave a lot of data that was presented and gave a variety of things that we looked at. And I'm just going to go into highlights without getting too deep into the data here. But the first was looking at variability in results for 10 different buildings that were basically identical designs, construction, same materials, same contractor. We expected to see that pressure field extension would look very similar between the 10 buildings, but this was probably the most surprising result is that we found that it wasn't. There was a wide variability. uh, Pressure field extension was acceptable within each building, but some buildings had much higher, stronger vacuum farther away than others. So we don't have a great answer as to why, but I think some theories, just differences in construction and the way these were actually built, the moisture that can get into the subslab, I think has a big role as well as the construction of the test ports. I think sometimes those can be jammed into the subbase or have water in them that can affect the results. Second, we looked at the effect of footers, or no, sorry, on of the gas permeable layer, the material that's used. Typically, you see a gravel. We do at least 4 inches of washed stone. In some of these buildings, we had a geocomposite drainage mat, like a dimple board shown in the lower right. So that forms a small void space that can be used as an alternative to gravel. What we found there is the gravel had better performance in terms of vacuum extension, which wasn't a surprise because it has a larger void space compared to the dimple board. Finally, we looked at the effect of footers and how those reduce the vacuum. If you've got a test port on the opposite side of a footer from your riser and there's no piping in between them, then obviously we would expect to see a decrease in vacuum across that footer because there's a break in the gravel layer. And that's exactly what we saw. So to varying degrees, there were differences there and the amount of reduction that we saw across the footer. In some cases, there's some vacuum extension across footers, but it's a significant reduction. So just wrapping up key findings that we saw. Number one, construction variability between 10 identical buildings. We saw big differences in the amount of vacuum propagation. Number two, the effect of the gas permeable layer material. One takeaway here is when we design systems with drainage mats instead of gravel, I think we'll probably decide to use tighter spacing in the risers than we might otherwise. Number three, the effects on footers, breaks in the gas permeable layer had a significant drop in vacuum across those. So when we're designing these systems, we account for that, making sure that we have pipes through footers and are providing vacuum influence to each isolated area of the subslab. So that's my last slide. Thank you very much.